Let us continue halogens. In the halogens, color of halogens we'll see. Fluorine shows yellow color, chlorine greenish yellow, Cl2 greenish yellow, bromine red, iodine violet. Iodine is giving violet color. Sorry, halogens are showing like this color. Why fluorine shows violet? Why fluorine shows yellow color? We'll see. Now we will take VIBGR. We'll take VIBGR. We'll take in the VIBGR. We'll take violet, indigo, blue, green, yellow, orange, red. We'll take. Now fluorine appears yellow because it is absorbing violet. Iodine appears violet because it is absorbing yellow. So iodine appears violet because it is absorbing yellow. Fluorine appears yellow because it is absorbing violet. It is fluorine is small size, iodine is higher size, therefore it is absorbing. Since the size is high, it is absorbing low energy color for excitation. It is small size, therefore it is absorbing higher energy color for excitation. Small size in the sense electron cloud will be tightly bounded, so it requires more energy for excitation. Therefore, it is absorbing higher energy violet light. Size is large, therefore electron cloud is loosely bounded. Therefore, it is absorbing lesser energy yellow color for excitation. Okay, therefore fluorine is absorbing violet, therefore it is emitting yellow color. Iodine is absorbing yellow color, therefore it is appearing violet color. Cl2 is greenish yellow, bromine is red color. Like this we are saying. Next, we will see oxidizing power. Next, we are seeing oxidizing power. Oxidizing power. Now, this oxidizing power, how to say experimentally? Experimentally, we are getting what value? In the sense E0 value we are getting, standard potential we are getting. So that standard potential, theoretically how to calculate, that we will see. Now fluorine oxidizing power we want to see. First it's a physical state, we will take fluorine physical state is gas. We have to convert this into atom. Okay, we have to convert this into atom. Then it has to be converted into oxidizing agent. Oxidizing power means it is oxidizing agent. Oxidizing agent means it undergoes reduction. Therefore, it gains electron and becomes F minus. Then it goes for hydration. Okay, these are the steps involved. So here it is called dissociation endothermic. It is called electron gain enthalpy. Taking electron. It is hydration enthalpy. So for this overall process, what is the delta H you take? Then T delta S you take. Delta S for the overall process you take. From this you get delta G. From delta G you get E0 cell. Okay, cell potential you get it. So like this only cell potential will be calculated. So for this E0 for fluorine, what is the E0 value in the sense 2.87 volt. Sir, oxidizing power is given in standard potential, that is 2.87 volt. Next we will take chlorine. Cl2, it is physical state is gas. First we will convert this into chlorine atom, then we will convert this into Cl minus gas, then it is into hydration. Okay, here dissociation, here electron gain enthalpy, here hydration enthalpy. So find delta H. From delta H we can find potential. The potential is, standard potential is how much? Means 1.36 volt. So fluorine you see oxidizing power is 2.87, but chlorine oxidizing power is 1.36. So which is having higher oxidizing power means fluorine when compared to chlorine. So now we will see first step in these two. First step is what in the sense bond dissociation. Now we will see bond dissociation enthalpy for fluorine. Now bond dissociation enthalpy for fluorine, we will see what is that value. Bond dissociation enthalpy of fluorine is how much in the sense 158.8 kilojoule per mole. 158.8 kilojoule per mole. For Cl2 242.242 kilojoule per mole. For Cl2 242.6 kilojoule per mole. It is bond dissociation enthalpy. Bond dissociation is endothermic. So bond dissociation enthalpy of Cl2 is more, for F2 is less. So easily dissociating, F2 is easily dissociating than Cl2. Therefore, we are saying oxidizing power is more here when compared to Cl2. Sir. Then electron gain enthalpy we'll see. Electron gain enthalpy for fluorine is minus 333 kilojoule per mole. It is minus means exothermic. For chlorine, minus 349. So electron gain enthalpy is exothermic for both, where it is high means chlorine. Electron gain enthalpy is high for chlorine, even then oxidizing power for chlorine is less. That means we should not see only electron gain enthalpy, we have to see overall process, overall delta G we have to see. Okay. Therefore, though electron gain enthalpy is high for chlorine, oxidizing power of chlorine is less only. Sorry. Next, hydration enthalpy we'll see. Now we will see hydration enthalpy. The hydration enthalpy is for fluorine is minus 515. Exothermic, minus means exothermic. Kilojoule per mole given. Chlorine is minus 381 kilojoule per mole. Hydration enthalpy is less for chlorine, high for fluorine. Therefore, fluorine is having higher oxidizing power than chlorine cell. Next, we will take a bromine. We will see. Bromine will take, it is in liquid state. First, we will convert this into gaseous state. Then we will convert this into atom. That means a dissociation of bond. Then we will convert into Br minus gas. Then into hydration. Therefore, Br minus aqueous. For this, we will see E naught. E naught for bromine is how much means 1.09 volt. Next, we will take a iodine. Iodine is in solid state. That we will convert into gas. Then we will dissociate this into atom. Then we will convert this into I minus. This into hydration. Okay, for this E naught. For this E naught is a 0.54 volt. Therefore, we can say that here F2 oxidizing power is greater than Cl2, Cl2 greater than Br2, greater than I2. Oxidizing power is like this is there. Oxidizing power like this is there, we are saying. Okay. Now we will see the reactions. Now we will take halogen F2. Halide is Cl minus I will take. What will happen? F2 oxidizing power is more. Therefore, F is undergoing reduction and become F minus. Cl minus undergoing oxidation and become Cl2. Okay, like this reaction possible. Similarly, we can convert Br minus into Br2, I minus into I2. Like this we can convert. So F2 can oxidize Cl minus, Br minus and I minus. Okay. Next we will see, we will take Cl minus, we will take F2. Now we have taken what in the sense Cl minus we will take, we have taken, and F2 reaction is possible or not means yes, possible. Sorry. Next reaction we'll see. We'll take a Cl2, F minus we will take. Chlorine is having less oxidizing power than F. Therefore, Cl2 cannot oxidize F minus. F minus cannot undergo oxidation. So no reaction. Now we'll take Br minus, we'll take Cl2. Chlorine is having more oxidizing power than bromine. Therefore, Br minus can undergo oxidation and becomes bromine. Cl2 undergoes reduction and becomes Cl minus. Similarly, I minus can be converted into I2. Okay. Next, we'll take bromine, we'll take F minus. Bromine oxidizing power is less, therefore bromine cannot oxidize F minus. Then we'll take Cl minus. Bromine oxidizing power is less than Cl, therefore Cl minus cannot undergo oxidation. Then bromine with I minus. Now bromine oxidizing power is more than iodine, therefore bromine oxidizes I minus. I minus undergoes oxidation and gives I2. Bromine undergoes reduction to give Br minus. So like this reaction possible. Set. Next, preparation of fluorine we'll see. Fluorine we cannot prepare by, that means fluorine we cannot prepare by chemical method. Why? Because F minus cannot undergo oxidation. If F minus undergo oxidation, then only we can get fluorine. F minus cannot undergo oxidation. Therefore, how to get fluorine? Not possible. Therefore, fluorine we can prepare only by electrolysis, not by chemical oxidation. Okay. Next, this halogens oxidation states we'll see. What are the oxidation states? It will show. That we'll see. Now, halogen general electronic configuration is what means NS2, NP5, Nd is 0. For fluorine, no Nd. For fluorine, d orbital will not be there in the valence shell. For rest of the halogens, d orbital is present in the valence shell. Set. Ns contains 2 electrons. Np contains 5 electrons. Np contains 5 electrons. In Nd, no electrons. Nd is not containing electrons. Sorry, it is ground state. So, if halogen gains 1 electron, it will show -1 oxidation number. If halogen is contributing this unpaired electron for chemical reaction, it is almost somewhat donating this electron for chemical reaction, then it will show +1. Now, first excited state we'll see. First excited state means this p electron is getting unpaired and goes to d orbital. It is not possible in fluorine. Okay, fluorine excitation is not possible. Okay, because d orbital is not there. So this electron is getting a unpairing and goes to d. In the first excited state, 3 unpaired electrons are there. If these 3 involved in chemical reaction, then it will show +3 oxidation state. Then second excited state will see. In the second excited state, this Np, this electron getting unpaired and goes to Nd. Goes to Nd. Now 5 unpaired electrons, therefore +5 is possible. In third excited state, how many unpaired electrons will get? 7. Therefore, +7 oxidation state is possible. Therefore, halogen can show general oxidation states like this. Fluorine, if you take, fluorine can show -1 and +1. Fluorine can show -1 and +1 only, but the rest of the halogens can show other oxidation states also. Next, we'll see halogens reaction with water. How halogens reacting with water, that we'll see. Fluorine react with water to give what, in the sense, HF and oxygen. Otherwise, even ozone also possible. Fluorine can give even ozone. Fluorine reacts with water to give HF, then oxygen will be obtained. Otherwise, ozone will be obtained. You see that here, which is undergoing oxidation, you see. Oxygen is undergoing oxidation. Fluorine is undergoing reduction. Okay. Then Cl2 with water gives what, means HCl and HOCl. Here, which is undergoing oxidation, that we will see. Chlorine oxidation number 0, Here chlorine is -1, here chlorine is +1. Chlorine undergoes oxidation and become +1. Chlorine undergoes reduction to -1. Oxygen oxidation number is not changing here. Chlorine is undergoing disproportionation reaction. Oxygen oxidation number same -2 only. Set. That means, but in this case, oxygen undergoes oxidation. That means fluorine is more reactive than chlorine. Fluorine is having higher reactivity than chlorine, we can say. Next, bromine. Bromine with water, we are getting HBr and HOBr, same like chlorine. So here also disproportionation. Iodine with water. Iodine with water gives Hi and O2. For this, delta G is plus 105 kilojoule per mole. Delta G is positive means it is non-spontaneous. That means not possible. This reaction is not possible. Therefore, but reverse is possible because delta G is negative for reverse. How the reverse reaction is possible, that we will see. Hi we can write H plus and I minus of O2. So what we are getting in the sense I2 and water. That means oxygen can oxidize I minus. So this reaction is non-spontaneous in the sense we can say down the group rate of reaction decreases. Reactivity, rate of reactivity. That means down the group reactivity of halogens decreases, we can say. So F2 is more reactive than Cl2. Cl2 is more reactive than Br2. Br2 is more reactive than I2. Like this we can say. This is a reaction with the water. Then reaction with the hydrogen, how it is there, that we'll see. Now fluorine reacts with the hydrogen to give HF. This reaction takes place violently even in dark condition. Violent reaction in dark. Dark itself violent. Then Cl2. Cl2 gives HCl. This reaction takes place in the presence of sunlight. Next we will see with bromine. Hydrogen reacting with bromine to give HBr. This reaction takes place in the presence of sunlight under the temperature 593 Kelvin. Then iodine reacts with hydrogen to give Hi. Here we need catalyst. We need catalyst. Temperature is how much? Means 713 Kelvin. Temperature is 713 Kelvin, we can say. So iodine, hydrogen reacting with iodine in the presence of catalyst at 713 Kelvin. So how the reactivity will be there down the group, you see, down the group rate of reaction decreases. Down the group reactivity decreases. That's what we can say. So next we'll take about hydrates. We'll take hydrates of halogens. How the melting point, boiling point, this and all will be there for hydrates of halogens, that we'll see. Now first we'll see melting point. We'll see melting point of HF is 190 Kelvin. HCl 159 Kelvin. HBr 185 Kelvin. Hi 222 Kelvin. So how the melting point varies, you see, from HCl to Hi, melting point increases because size increases, van der Waals force increases, therefore melting point increases. From HF to HCl, melting point decreases because HF hydrogen bonding, in HF hydrogen bonding is there, in HCl van der Waals force is there, therefore HF is having higher melting point when compared to HCl. Sir, here what is the order of melting point? Order of melting point, if you see, HCl greater than HBr greater than HF greater than, here HF comes where in the sense HBr value, HF comes where 190 Kelvin. So it is 159 means it is less value. So we have to say that HCl melting point is less, we have to say. HCl melting point is less than HBr, HBr less than HF, HF less than HI. Like this melting point order is there. Okay. Next we will see boiling point. Boiling point for HF, HCl, HBr, HI. Boiling point order we will see. Boiling point for HF 293 Kelvin, HCl 189, HBr 206, HI 238. So what is the order of boiling point? That we will see. From HCl to HI, boiling point increases because van der Waals force increases. From HF to HCl, boiling point decreases because in HF hydrogen bonding is possible, in HCl van der Waals force is possible. That's why. Then we'll see the bond length. We'll see HF bond length is 91.7 picometer. HCl bond length is 127.4 picometer. HBr 141.4, HI 160.9. Down the group bond length increases because size of halogen increases, we can say. Next, bond dissociation energy. Now HF will take in the gaseous state. To dissociate this, to break the bond, what is the energy required? In the sense 574 kilojoule per mole. Then bond is breaking, hydrogen becomes gaseous atom, fluorine becomes gaseous atom. So to break the bond, we are supplying this much energy for 1 mole. Now we will take HCl. To break the bond, how much energy we are supplying, we will see. For HCl 432 kilojoule per mole, the bond is breaking, we are getting hydrogen atom in gaseous state, chlorine atom in gaseous state. So bond dissociation energy is more here, less here. Why? Because size is small, therefore overlapping is more extent, bond strength is more. Size is high, overlapping extent is less, bond strength is less. Next we will see HBr. For HBr, bond dissociation energy is 363. For HI, bond dissociation energy is 295. So down the group, size of halogen increases, extent of overlapping for the formation of bond increases. So bond strength, overlapping extent, what happens means decreases, we have to say. Bond strength decreases, therefore bond dissociation energy decreases. So now we will see acidic strength. What happens to acidic strength? Acidic strength we will see. Now for HF, pKa is how much? Means 3.2. For HCl, pKa is -7. pKa is -7 means Ka is equal to 10 to the power of +7. 10 power +7. pKa is -7 means Ka is 10 power +7. 10 power +7 in the sense Ka is very large, therefore HCl is strong acid. HBr, pKa is -9.5. HI, pKa is -10. That means Ka is equal to 10 to the power of 10. So pKa is 3.2. That means it is weak acid. HF is weak acid. So we can say HF is weak acid. HCl, HBr, HI strong acid we can say, because 10 power 7 for HCl, 10 power 10 for HI. So down the group, what happens to the acidic strength? Down the group, acidic strength increases. Acidic strength increases. This we cannot explain using electronegativity. Using bond dissociation energy we can explain. Down the group, bond dissociation energy decreases. That means here we can break bond easily, therefore it is giving H plus easily, therefore its acidic strength is high when compared to others. So down the group, bond dissociation energy decreases, Therefore, acidic strength increases, like that we can say. Next, KHF2. KHF2 existing, whereas KHCl2 is not existing. Why is it so? How to prepare KHF2 means take KF and add HF, we will get KHF2. KHF2. How? We will see. KF we can write it as K plus 1, F minus 1. HF we can write it as HF, like this. Here we will give partial bond, partial plus, partial negative. Now this F minus is attracting this H plus through hydrogen bonding. Because of hydrogen bonding, KHF2 is existing, K plus HF2 minus is existing. But here hydrogen bonding is not possible, therefore it is not existing. Therefore, if you mix KCl and HCl, you will not get KHCl2 because no hydrogen bonding. Therefore, like this not possible. Sorry. Next, we will take anhydrous HCl. We are taking anhydrous HCl. Anhydrous HCl is bad conductor because it is covalent. But aqueous HCl is good conductor because it is ionic. In aqueous HCl, it is existing in the form of H3O plus ions and Cl minus ions. Because of ionic, it is conducting electricity. So aqueous HCl is good conductor, whereas anhydrous HCl is bad conductor because it is covalent. Here covalent nature is around 83% is there. Okay. Next we will see oxyfluorides. Next we are going for oxyfluorides. We will take OF2, we will take oxyfluorides. Why fluorides? In the sense fluorine will take negative oxidation state, oxygen will take positive oxidation state. Okay, OF2 we will write like this. OF2 we are writing like this. Oxygen oxidation number is +2, fluorine is -1. Therefore, it is called fluorides. We should not say oxide, we should not say. This is stable at 298 Kelvin, we can say. It is stable at 298 Kelvin. Here bond angle is how much? In the sense 103 degree. Bond angle is 103 degree, we can say. Next we will take O2F2. O2F2 we can write like this. O2F2. Here oxygen oxidation number is, we can say, +1, fluorine is -1. Here why the year -1 means this bond we have to shift to fluorine because fluorine is having high electronegativity. Therefore, it is getting -1. It is losing the bond. Therefore, it is getting +1. Both are having same electronegativity. Don't shift this bond. With respect to this bond only, we have to say charges. Okay, higher electronegativity. So shift this bond completely towards F. So fluorine will get -1, oxygen will get +1. How to say shifting means? To say oxidation number, what we have to do means assume that we are shifting the bond completely towards more electronegative atom. Like that assumption you think, keep it in mind and say the charge to say the oxidation number. It is having high electronegativity, so we are shifting this bond towards fluorine. Therefore, this bond is going towards fluorine. So this bond is gained by fluorine. That means fluorine gains 1 electron, so getting -1. So oxidation number of fluorine in O2F2 is -1, whereas oxygen is fluorine +1. This bond we should not shift because both have same electronegativity. Okay, this bond alone is shift to fluorine, so give fluorine -1, oxygen +1. So O2F2 structure is same like hydrogen peroxide. This O2F2 is unstable solid. It is used for fluorinating agent. It is used as fluorinating agent. It is used as oxidizing agent. Then this one with the plutonium with O2F2, we are getting what? In the sense plutonium becomes PuF6. Okay, so now we will take in the spent nuclear fuel. In the spent nuclear fuel, that means nuclear fuel used up nuclear fuel is called spent. In that plutonium will be there. To separate that plutonium, this is treated with O2F2. Plutonium becomes PuF6, which is gas which comes out, which we can collect it. Okay. Next, we will see oxides of chlorine. We will see oxides of chlorine. In the oxides of chlorine, first one we will take chlorine monoxide, Cl2O. This with water gives hypochlorous acid. Therefore, we can say it is anhydride of hypochlorous acid. We can say. Then this structure will see oxygen at center. Chlorine will give us surrounding atoms. Here lone pairs will give for oxygen. Here what is the bond angle? Here bond angle is 111 degree. Bond angle we can say 111 degree. Why bond angle is 111 degree means chlorine size is larger. Chlorine size is larger. Actually, this oxygen is having 4 electron pairs. 4 electron pairs means 190 to 28 minutes. Lone pairs present means less than 190 to 28 minutes, we have to say. But here, greater than 190 to 28 minutes is there due to larger size of chlorine. Okay. Next, we will take ClO2, chlorine dioxide. We are taking ClO2. This name is called chlorine dioxide. This chlorine dioxide, to this if you add water, you will get HClO2 and HClO3. Therefore, we can say HClO3 we can say. Now, it is anhydride of chlorous acid and chloric acids we can say. This structure will see chlorine and 2 oxygens we have drawn. Chlorine valence shell contains 7 electrons. That 7 electrons will give. Okay, oxygen valence shell contains 6 electrons. That 6 electrons I am giving. Now we will go for bonding. Here double bond is possible. Here dative bond is possible in ClO2. Next, what happens means this electron is entering into this bond. So this electron is disappearing and entering into which place in the sense of bond. So this bond is containing 3 electrons. Therefore, we can say it is a odd electron bond. Okay, this molecule is odd electron molecule. We can say because of odd electron, it is paramagnetic. Then this is used as bleaching agent. Here, what is the bond angle means? Bond angle is 118 degree. Now, here if you see 2 sigma bonds are there, 1 lone pair is there. That means 3 electron pairs. 3 electron pairs means 120 degree angle. Due to lone pair less than 120 degree, that's what it is having. Okay. Then chlorine hexoxide will see Cl2O6. Chlorine hexoxide, we will treat this with water. We are getting chloric acid HClO3 and HClO4 perchloric acid will get. Therefore, we can say it is anhydride of chloric acid and perchloric acid we can say. This structure we will see Cl2O6 structure. 2 chlorine will write. For each chlorine, we will give 3 oxygen atoms. Oxygen will make double bond. Oxygen will make double bond with the Cl. So double bond you give. Between Cl, you give single bond. Chlorine comes under 7th A group. Therefore, it can form 7 bonds. So 7 bonds is there here. Next, we will take Cl2O7. Cl2O7 will take. This we will treat with the water. So what we are getting means HClO4 we will get. Therefore, it is anhydride of perchloric acid we can say. This name is chlorine heptoxide we can say. This structure will see. We will take 2 chlorine and 7 oxygens are there. For this chlorine 3 oxygen. For this chlorine 3 oxygen. 1 oxygen common for both. Then we will give bond here like this. Oxygen makes double bond. Oxygen is making double bond. Now we can say these double bonds have 1 bond length. These single bonds have 1 bond length. Therefore, ClO bond length 2 values possible for this we can say. Next, we will take oxides of bromine. Oxides of bromine, what are the possibility in the sense? Br2O is possible, then BrO2 is possible, then BrO3 is possible. Okay. Oxides of bromine is having least stability among the oxides of halogen. Which is least stable means oxides of bromine. These oxides of bromine exist only at low temperature. Oxides of bromine act as powerful oxidizing agents. Then we will see oxides of iodine. Oxides of iodine is what are the oxides of iodine means I2O. Oxides of iodine will take, that is I2O3 will take, then I2O5 will take, then I2O7, oxides of iodine. This I2O5 is a good oxidizing agent, therefore it is used for estimating carbon monoxide. How we will see iodine pentoxide reacts with carbon monoxide to give what in the sense iodine and carbon dioxide. We will balance this like this. Okay. Now this iodine and the amount of iodine we can find using titration with hypo. So hypo is titrated with iodine. From that titration we can find number of moles of iodine. From number of moles of iodine we can say number of moles of carbon monoxide. Therefore, this I2O5 is used for estimating CO, we can say. Then order of stability of oxides we will see. Order of stability of oxides, I is greater than Cl is greater than Br, like this is there. Then higher oxides and lower oxides we will see which is more stable, means higher oxides are more stable than lower oxides, we can say. Then reaction with alkalis. Halogens, how halogens reacting with alkalis we will see. Now we will take F2 with then base we will take alkali. Now condition is cold and dilute. Condition is cold and dilute. We will take, what happens means F2 is converting into F minus. Then we are getting OF2. Oxygen here -2 oxidation number becomes +2. -2 is the oxidation number of oxygen. Here oxygen oxidation number is +2. Sir. Next, fluorine with a hot and concentrated alkali. Hot and concentrated alkali we'll see. So F2 becomes F minus. Then here O2 is obtained. Here oxidation number 0, here -1. Oxygen oxidation number -2, here 0. So cold and dilute alkali if we take, we are getting OF2. Hot and concentrated alkali if we take O2, we are getting F2 is converting into F minus. Here which is undergoing reduction means F2, which is undergoing oxidation means oxygen. In this case, oxygen is converting into +2. Here oxygen is converting into 0 oxidation number. Okay. Next, chlorine we'll see. Now chlorine chemical property we'll see. Chlorine we will take, then alkali we will take, cold and dilute we are taking. Cl2 is converting into Cl minus and ClO minus. Here chlorine oxidation number is 0. Here chlorine oxidation number is -1. Here chlorine oxidation number is +1. That means disproportionation reaction is possible. Then chlorine with a hot and concentrated alkali we will see. Chlorine with hot and concentrated alkali, what happens means Cl minus and ClO3 minus is possible. Here oxidation number -1, here oxidation number +5. Chlorine undergoes disproportionation. Similarly, bromine and iodine. Bromine and iodine is same like chlorine. Here what will be possible? Br minus. Here BrO minus. Here Br minus. Here BrO3 minus. Here I minus, IO minus. I minus, IO3 minus. So Br2 and I2 follows like Cl2. So Cl2, Br2, I2 in one manner reacting, but F2 in another manner. In Cl2, Br2, I2 disproportionation reaction. But in fluorine undergoes reduction, oxygen undergoes oxidation with alkali. So reaction with alkali like this is there, we are saying.